Over the last 4 weeks, our main focus has essentially been to gain an insight into the physics of semiconductor, utilize this knowledge to understand the principle of operation of a semiconductor diode and its working as a diode laser. However, before we move any further, it may be worthwhile at this point to briefly summarize whatever we have learned thus far in the area of semiconductors, its working as a semiconductor diode, and the ability of a semiconductor diode to emit both conventional as well as coherent light. You see, the energy levels of an isolated atom, we know very clearly, that can be represented as so. This is the outermost energy level, and these are the inner. The electrons residing in these inner levels, for example in this level, is closest to the nucleus and therefore is very strongly bound to the, quite rigidly bound. On the contrary, the electrons in the outermost shell is the farthest from the nucleus and is therefore rather loosely bound, and therefore electrons in this shell, energy shell, is relatively free to move around. So this is for an isolated atom. Now when you pack up these atoms very densely together to form a solid, then the outermost energy level, actually the wave functions of the electrons residing in this outermost level of different atoms, they overlap quite significantly, and this results, as we have seen, in splitting of this energy levels. And in a solid where huge number of atoms are packed together, the energy levels then essentially is broadened. The inner energy levels, on the other hand, have very insignificant overlap with the wave function of the other neighboring atoms, and thus remain just as in case of an isolated atom. So this is in a solid when atoms have been closely packed. Now, for a material to behave like a metal which is metal, this outermost energy, which is now a band, is only partially filled with electrons. This is called conduction band. As it is partially filled with electron, there is a lot of energy space which is empty. Therefore, upon application of a very modest voltage, the electron can acquire electrical energy from that voltage, from the potential difference, and can easily move in this region in the energy, thereby constituting a current very easy. And that is why a metal shows conduction, and this is known as conduction band, where the electrons can easily move upon application of a modest voltage across the two ends of, say, metal plate. So when this material will behave like an insulator, For an insulator, on the other hand, this energy band is completely full with electrons. And therefore, quite unlike metal, these electrons which are residing here, they cannot acquire upon application of that modest voltage, as in case of metal, they cannot conduct electricity because there is no energy space available for this electron to move, to acquire energy and move from that applied potential difference of the electric field. The only way it can conduct is for the electrons which are here, to actually go up to the next energy state, which is again empty, which is unoccupied. However, the energies difference between this level, which is now called valence level, and the next energy level, which is located above the valence level, is extremely large, the energy separation, which can be several electrons, or say 10 electrons. And therefore, for an electron to cross over from this valence band to this, and once the electron comes here, this electron will be able to easily conduct electricity in this upon application of very little potential difference, because this is again empty. So in this case, this will be the conduction band, as electron appearing here would be able to conduct electricity. This is the valence band, where electron cannot conduct. Now, the thermal energy, which is omnipresent, say at room temperature, ambient condition, is about 0.025 electron, which is much too less compared to this forbidden energy gap. And therefore, with the thermal energy that the electron can have here, this kind of thermal energy, it cannot make a transition from valence to the conduction band. And that is why an insulator, and the other way that the electron can go here is by application of electric field. So upon application of an electric field, the electron here will experience force, and if the force is good enough, then it can actually move the electron from the orbit corresponding to this energy level to the orbit corresponding to this energy level. However, for a typical insulator, the field that would be required is maybe even 100 million volt per meter, which is absolutely impractical. And that is why an insulator would not conduct electricity under normal circumstances. So now in this, let us see what will be a semiconductor. So in case of semiconductor, too, like insulator, the outermost energy level, that is valence level, valence energy band, valence energy band is completely full with electron. However, the next energy level, which has the potential to perform as a conduction band, lies in the immediate vicinity of the valence band. That is the property of that material. And this can be as small as even less than 1 electron volt, even much less than 1. And therefore, even at low temperature, even though at low temperature, the electron may not have even that kind of energy to cross over. But as you raise the temperature, that is at ambient temperature or even little higher temperature, a good fraction of the electrons will have enough thermal energy to cross over to the conduction band from the valence band. And once the electron comes here, it can easily conduct electricity at application of a modest potential difference. between the two ends of the semiconductor of this material. Such a material is called a semiconductor. But quite unlike metal, which conducts electricity only in its conduction band, a metal is a semiconductor is very different, because you see, when we say that an electron has, so this is valence band is completely occupied with electrons. So let us consider one electron, and with the thermal energy it has been able to cross over, jump over to the conduction. So this electron has come here. So it has actually left an empty space here. This is, the electron has moved away from it. So it has come here and it's created a corresponding empty state here, which is called hole. And as it is actually represents deficit of electron, that means it has a positive charge. The electron is negative. And when you apply a potential difference to a semiconductor, right, the electrons will conduct electricity in the conduction band. Suppose the polarity is such that the electron moves in this direction, the hole will move in the opposite direction in the valence band and would conduct electricity. Correct. Therefore, the conduction in a semiconductor arises from the motion of both electrons in the conduction band, and holes in the valence band. These holes in the valence band. This makes semiconductor significantly different from that of metal. And such semiconductors, which naturally shows this behavior because the conduction band is very close to the valence band, are called intrinsic semiconductors. Intrinsic semiconductors. The two most, and this semiconductor can be both of elemental type as well as compound type. Elemental means when, as I said, when the atoms form the solid and you have semiconductor. So the two significant or most popular semiconductors, atomic semiconductor, elemental semiconductors are silicon and germanium. And some of the common examples of molecular semiconductor, compound semiconductor is gallium arsenide, indium phosphate, gallium phosphate, aluminum phosphate, and many more. Interestingly, gallium arsenide and indium phosphate are the most popular semiconductors for which have been used to fabricate semiconductor lasers. So these are all intrinsic semiconductors. It has naturally has this ability. However, the conductivity can be tailored in a remarkable manner if the intrinsic semiconductor is doped by a trace quantity of some certain type of impurities. For example, I show you a silicon semiconductor, which is the most one of the most popular semiconductor. Silicon has 4 electrons in its outermost shell, and therefore you see in the when the crystalline silicon is formed, each silicon is actually the 4 electrons are bonded with the electrons provided by the neighboring silicon, and therefore they are all bound. However, in an intrinsic semiconductor, as you know, that even little thermal energy, which is omnipresent, can result in one of these electron to cross over to the conduction band from the valence band and conduct it. That is the intrinsic semiconductor. However, if you dope this silicon crystal with, say, arsenic atoms in a trace quantity, the quantity can be so small that silicon to arsenic concentration can be to the scale of 10 to the power 6 to 1, or even more than 10 to the power 6. That is 1 in 10 or 100 million silicon is replaced by arsenic. Now, arsenic has 5 electrons in its outer shell, and therefore when arsenic replaces a silicon, 4 of the electrons of the arsenic gets automatically bonded with the 4 electrons provided by the neighboring silicons. This thus leaves one silicon unoccupied, unbound, and therefore it is relatively free to move in the conduction band. And such a semiconductor is called extrinsic semiconductor. Extrinsic semiconductor. Such a semiconductor is called extrinsic semiconductor. And the majority of the charge carriers here will be electron, which is donated by this arsenic. And its conductivity can be significantly higher than what is possible from the intrinsic crystalline silicon. And as you can see, that this is called N-type semiconductor, and as you can see that majority of the charge carriers in an N-type semiconductor is electrons, which are basically donated by the arsenic, that is the dopant molecule. The few holes that you see in the valence band, these are actually the holes which are formed intrinsically by the intrinsic property of the silicon semiconductor, because with some thermal energy, the electrons which are present here actually blows up and created this hole. So these 2 electrons are actually contributed by the intrinsic silicon, and rest of the electrons that you see in this are actually contributed, donated by the dopant arsenic. Nevertheless, in a N-type semiconductor, the majority of the charge carriers is therefore electron, and this electron will conduct the conduction band, while the few holes that have been created, that anyway would conduct in the valence band. So this is an N-type semiconductor. Now if you dope it with gallium instead of arsenic, then the gallium has 3 electrons in the outermost side. Therefore, if it has to make 4 such bonds, then 1 electron will appear from somewhere, and you can always perceive it as if the electron has disappeared from it, forming a hole. Thus, you see, like arsenic donated electron for conduction in the conduction band, the gallium here donates hole which will conduct electricity in the valence band. Thus, and such extrinsic semiconductors are called p-type semiconductors, where the majority of the charge carriers are holes, and few electrons that you see in the conduction band, they are basically the holes, basically the electrons that has intrinsically got excited from the valence band to the conduction band as a result of thermal energy. So this electron which was present here, it actually, by the thermal energy, it made a transition to the conduction band. So these two holes have been contributed intrinsically by silicon, and rest of the holes have been contributed, donated by gallium. So this is called p-type semiconductor. However, when a p-type semiconductor joins with an n-type semiconductor, then the semiconductor reveals its most interesting property and makes possible the device kind of application of semiconductor. And the most simplest of such devices is a p-n junction. That is, when you connect a n semiconductor, n-type semiconductor with a p-type semiconductor, then the junction, you see, very interesting phenomena occurs. So joining the p and n-type semiconductors adds a new dimension to the semiconductor, paving the way, as I said, for their device application. So let us take a deeper look. Now, left to itself, some of the free electrons which are present here will diffuse through this junction into the p region, will tend to diffuse, and the free charge carriers, holes, will tend to diffuse into the n region through this junction barrier. Now, as they meet at the junction, the electrons will automatically jump into the hole and disappear, and the charge carriers should disappear. This leaves the immediate vicinity of this junction with a layer of positive ions in the n region and a layer of electrons in the p region. This sets up a local field which prevents, this establishes a thin region in the vicinity of the junction that is devoid of any carrier, called a depleted region. Where this charge separation sets up a local field that opposes any further diffusion of the charge carriers across the junction. This establishes a region which is devoid of any free charge carrier. This is called depleted region. Now this depleted region actually makes possible a p-n junction to perform as a diode. When you bias this p-n junction in the reverse way, that is, you connect the n region to the positive terminal of a battery and p region to the negative terminal of a battery, there will be momentary flow of current as the free electrons from the n region and free holes from the p region flow away into the battery and annihilate each other. This quickly results in the depletion of charge carriers on either side of the junction, thereby causing a stoppage of flow of current through the circuit almost instantaneously. So in this, if you bias it this way, then current cannot flow through this device. Now, if we bias it the other way, that is forward bias, that means you connect the n region to the negative end of the battery and p region to the positive end. Then what happens? The battery now clearly pumps electrons in the n side, in the n region, and pumps hole in the p region. The holes and electrons then continue to meet at the junction and annihilate each other in the junction region, that is in this depleted region, maintaining a steady flow of current to the circuit in this configuration, which is known as forward bias. And if you increase the voltage, that is, if you increase the voltage, more current will tend to flow because it will pump more and more electrons in the N side and holes in the P side. So this is called forward, and this is the reverse branch. So it behaves like a diode because it allows current to flow in one direction and no current to flow in the other direction. Now, the most interestingly, this diode can actually emit light. You see, when we say that this is a conduction band and this is a valence band. Now, as you have forward biased it, that means you are pumping electrons in the conduction band and holes into the valence band. So suppose we just consider you have put an electron here that is in the conduction band and one hole in the valence band. Now they have now appeared in the depleted region. So where the electron will drop down into the valence band, combine with this hole and will disappear. So what does it mean? It means that the electron, this is the forbidden energy. Suppose we call it delta E. So electron, when it comes down to the valence band, it loses delta energy. So this energy can very well appear as a photon. So if the photon's frequency is nu, then the photon's energy h nu must equal delta E. So that means a diode, when it is forward biased, can emit light. And if that means, and this light would be emitted, this is spontaneous emission. So if you have this PN junction, this is the depleted region, and this is P, so you have connected it to the positive end of the battery, and this is N, you have connected it to the negative end of the battery. So the current will flow, and from here, photons will emit. I'm showing this in two dimensions, but in reality, photons will be emitted in all possible directions over the entire 4 pi solid angle around this. So this is called light emitting diode. However, for light emitting, I will not come into the all semiconductors cannot emit light, because for emission of light it has to be a direct band semiconductor, direct energy band semiconductor, direct energy band semiconductor, direct band semiconductor. Direct band semiconductor, only then this process will ensure conservation of both energy as well as momentum. In case of indirect band semiconductor, the momentum conservation is not guaranteed, and therefore it doesn't normally emit light, and this heat energy is actually dissipated as heat. That only ensures conservation of both energy and momentum. Unfortunately, silicon, the most popular semiconductor material, is an indirect band gap semiconductor and therefore does not show this property. Now, the important point is that if the light emitting diode can emit, can give out light spontaneously, then we know now clearly that the structure, that some of the photons that emits in a particular direction, say if we have formed a cavity, they can seed the stimulated emission. And if there is population inversion, and if you can integrate this population inverted medium in a cavity with a cavity, then there is a possibility that you will generate coherent light. So I will stop here tomorrow we'll just spend a little time seeing how this light emitting diode can be made to function as a semiconductor, for which of course you have to ensure that you have created population inversion, and you have been able to integrate this with a cavity to obtain amplification of, which would be nothing but a semiconductor.